I would like.
First of all, welcome everybody to our Gamma seminar. Today we have the pleasure to guest Alfred Michel Grundland from the Center de Recherche Mathématiques, Department of Mathematics of the Informatique of the Université Trois-Rivières. So, Michal, thank you for accepting our invitations, and thank you for talking about the Riemann wave superposition for the Euler system. And the floor is yours. Please go ahead.
Okay. Thank you very much. I would like first thank the organizer and thank the chairman, Professor Javier de Lucas, for inviting me to give me such an opportunity. What I would like to present some recent result which was obtained in last 2 years. This result was obtained in cooperation with Professor Javier de Lucas, first part, and second part with my postdoc, Łukasz Homenia. He is from Finland. Okay, the subject of this talk is on Riemann wave superposition obtained from Euler system. Now I would like to, that is the subject. Now I would like the outline. So I will recall a certain notion like Riemann invariant, Riemann wave solutions. Next, I will say some word about straightening of vector fields. Next, I will provide the definition of quasi-rectifiable family of vector fields. Next, I will discuss the rescaling theorem, and based on it, I will discuss the elastic and non-elastic wave superposition. And I will give some characterization of the quasi-rectifiability. Next, I will discuss a compressible non-stationary Euler system, and in this context, I will introduce the C infinity Lie module as an infinite dimensional Lie algebra. Based on it, I will rescale Lie modules. And this allows me to find a parametrization of the region of non-elastic superposition. And this fact allows me to reduce the form of the Euler system to the case of non-elastic superposition of waves. So this is what it's about. Now the objective, there are 3 objectives which I just mentioned. So to establish the condition for the existence of non-elastic and non-elastic superposition of wave governed by the Euler system, to analyze Lie module associated with the Euler system as an infinite dimensional Lie algebra, and to find the reduced form of the Euler system, describing non-elastic wave superposition. So let me first recall some notions. So I will start with a quasi-linear hyperbolic first order system in P independent variables x1, xp, and Q dependent variables u1, uq. I will denote the derivative dui by the partial derivative dui with respect to dxe by ui with the index. The quasi-linear hyperbolic system can be written in abbreviated way, that is ai of ui equal to 0. A are matrix A1 up to AP are matrix function of U only, I will assume. All considerations are local. So I will subject the initial system with a differential constraint. I will assume that all first derivative du alpha with respect to dxi are decomposable. Decomposable in the sense that is a linear combination of vector gamma and lambda with non-constant coefficient xi of x. The vector gamma and lambda satisfy the eigenvalue problem, which is given here. So you solve the determinant for one component of lambda, you substitute in the wave relation, and you determine the eigenvector. So it's typical eigenvector problem. Now, the functions u1, uq, xi1, xik are considered as an unknown function of x. Now, let me recall the Riemann wave solution. The Riemann suppose that gamma and lambda satisfy the algebraic equation. Let f be integral trajectory of the vector fields gamma parametrized by r. Let phi be arbitrary function of one variable. The implicit relations between the variables u, r, and x given by the expression u f of r equals some function lambda I xi, I use here the summation convention, can be solved so that the variables u, r can be given as a graph over the independent variables. Then the composed function u f of r of x constitute the simple Riemann wave of the initial system. The function r of x is the Riemann invariant. The proof is the proof of it. It's directly by differentiation. du alpha with respect to dxi is proportional to vector gamma and lambda with the coefficient xi of x, which is why I mentioned this proof, because it's related with the profile of the wave. And here the profile of the wave is completely arbitrary of the Riemann wave. Now we have the question, what is the result of the superposition of Riemann wave? First question. Second question, can we describe the result of superposition well by a simplest system? That is what it's about. Now, since we add a differential constraint, so the right-hand side is algebraic, we have compatibility condition for second-order derivative, because the first-order derivatives are decomposable. So the involutivity conditions were established in 1971 by Zbigniew Peradzyński, found the necessary and sufficient condition for existence of K waves with the freedom of K arbitrary function and of one variable. It requires that the commutator of each pair of vector fields, gamma I, gamma j, is spanned by this field. So that is a condition on vector gamma. The second condition is on vector lambda, that the Lie derivative along of covector lambda along the vector gamma is spanned by the vectors lambda I, lambda j is the second one.
Sorry,
So
Michal.
we have, yes.
Sorry. Peradzyński, is this guy I know from IMPA, or is another one?
No, it's Zbigniew Peradzyński from the Department of Mathematics.
Ah, okay.
He gave a talk in last year.
Yeah.
Okay, to don't be too technical, I will limit myself to the case 1 + 1 dimension. Why? In this case, you have the condition on lambda are identically satisfied. Now, the Frobenius theorem is not sufficient to prove the existence of an appropriate rescaling of the vector fields by some function h1 up to hk. So I such that the rescale functions they commute between them, and I would like to shed some light on this fact. So now the straightening of the vector fields. This is work based with U heavy. So let x1, xr be a family of vector fields defined on n-dimensional manifold, such that x1, xr are linearly independent in any point on the manifold n, there exists a coordinate system x1, xn, x on n, such that the first integrals of each vector field are given by the equations. Here you have k are the some constant, and we skip xi. And this equation holds if and only if the commutator of this vector field xi, xj are spanned by this vector field with certain function fij defined on n. Not necessarily constant. That is first. Now I would like to define the a family of vector fields x1, xr on n dimensional thing is said to be quasi-rectifiable if there exists a coordinate system x1, xr on n such that each vector field have the form. So xi is certain function g of x1, xn, and you have the derivation along only one direction. Here there is no summation with respect to I. These vector fields are linearly independent at any point on n. If it is not the case, otherwise, the set of vector fields we call non-quasi-rectifiable. This definition is base dependent. Now, a Lie module is quasi-rectifiable if the given basis is quasi-rectifiable. A Lie algebra is quasi-rectifiable if there exists a quasi-rectifiable basis. That is the difference. Now, let me introduce the rescaling theorem. So let x1, xr be a family of vector fields defined on n-dimensional manifold such that x1, xr are linearly independent at any point n. And each pair of vector fields, xi, xj, are such that the commutator of this vector field is spanned by this field with non-constant coefficient fij. Then there exists a set of a function, non-vanishing function, that we can rescale the vector field xi, xj in such a way that the rescale vector field commute between themselves. The way how we found the rescaling function is based on the theorem that you have a set of vector fields which span the distribution, let's say D. You find the dual one form to the set, respectively, and the rescale one form, the differential of rescale one form, restricted to this differential, to this distribution, have to be exact, have to be equal 0, how it was found. And all this work was done with Professor De Lucas.
By the way, Michel, just one curiosity maybe is interesting for our colleagues from Spain is that when we studied these Lie algebras with quasi-rectifiable bases that we classify all up to dimension 4, we had conditions that they were, in some sense, the contrary to obtain contact structures of left invariant forms on these Lie algebras. It was one work, I remember that we got one of the results, and when one equation was satisfied, we used this equation for in a work with Xavi Ribas to classify contact structures, like invariant contact groups. And when it wasn't very fine in a certain sense, it was to study this quasi-rectifiable. So it was kind of interesting that these problems were kind of dual to each other. That's all. That's maybe it's interesting for some.
Thank you, Javi, for this comment. I would like to have the reference for it. Okay, so let me come back to this. Now, suppose that the vector gammas are linearly independent and commute between themselves. Then there exists a parametrization of the k-dimensional parameter. You can parameterize the surface, k-dimensional function, with parameter R1, Rk. So to obtain this parameter, to obtain this surface, you have to integrate q by k partial differential equation. So df alpha with respect to dr have to be equal to the rescale function vector gamma. So we found the parametric form of the this integral surface. Now, the set of implicitly defined relation between r and x given by the lambda ixi equals some function of r can be solved such that r can be given as a graph over the independent variables. If so, we can write the solution as a composed function, that f is a function of r1 rk. And this constitutes a Riemann k-wave, and R1, Rk are the Riemann invariants. That is also a result by Peradzinski, this one. Now, I would like to discuss a new element, which I would like to provide. It is related to elastic and non-elastic superposition of wave. So I will introduce a new set, M, which I call the region of superposition of two waves corresponding to gamma 1, gamma 2. I will denote M, it's a subset of R2, is the set of x of t, such that the intersection of the support of xi, xi1 and xi2 is non-empty for some interval t, which belong to T minimum and T maximum. T minimum means where start the superposition, T maximum when the wave separates or when the superposition end up. It depends of the region of influence in the region of the uniqueness. Okay, that is the set M. Let M epsilon be a turbular neighborhood of the region M. Let M2 epsilon be a turbular neighborhood of the region M epsilon. Let us define a set A epsilon, which is the difference between these two sets, M2 epsilon minus M epsilon. Let B delta be a ball with a radius delta. Let phi j be a flow of the vector field gamma j. Now, let me define the set of two entering waves. I will denote them by gamma plus. Is the set of gamma such that the differential is decomposable. There exists a ball which is contained in the set A alpha such that the image of this ball by phi j, by the flow, is contained in the region of superposition, in the image of the region of superposition by U. That is the set of entering waves. Now the set of leaving waves for several waves. So it's a set of gamma such that the differential is decomposable. There exists a ball which is contained in the region of superposition M, such that the image of this ball by psi j is contained in the image of the set A epsilon by U. T belongs for some interval from 0 to capital T, which means T below the region of interaction. Here I made a picture of it. So you see the region M, the region M epsilon. You see the region of entering wave, gamma plus, which is from A epsilon to M, and the leaving waves from M to the region of M epsilon. I represent in this form. It's convenient. Now, I would like to provide the index of the region of superposition of two waves. So it would be denoted by gamma m, and it is difference of the cardinality of leaving waves minus cardinality of entering waves. The index gamma m, it is an integer greater or equal to 0. The index gamma m is independent of the function psi1, psi depends
sorry,
only.
Michal. Sorry, one
Yes.
question. What is for you the cardinality of gamma minus gamma plus? What does it mean?
I give the definition below. You can see the one. You say that a set has cardinally x equal to n.
Yeah, I see. Sorry, I see.
If you have bijection between these two sets. So you have bijection between the set of gamma, let's say plus or minus, with integer numbers. That is what it's about.
Thank you.
Okay. Please interrupt me whenever you have a question. Okay, so let me come back. The gamma m, the index, does not depend on the function size, but depends only on the vector fields gamma 1, gamma k. The region gamma m with vanishing gamma m preserves the type and the number of waves. And gamma m is invariant with respect to diffeomorphism on m. Now, the next definition. Suppose that we have a two wave, or W1, W2, which correspond to gamma 1, gamma 2. And they are either elastic if gamma m is equal to 0, or non-elastic if gamma m is greater than 0. So now is the question, how to relate this type of superposition with quasi-rectifiability. So I will provide some elementary theorems for vector fields. So the first theorem would be the superposition of two waves, W1, W2, associated to gamma 1, gamma 2, respectively, are elastic. The superposition is elastic if and only if the vector fields gamma I and gamma j are quasi-rectifiable. Second theorem. You have a set of vector fields x1, x2, x2, see? So a family of vector fields defined on R3. And we assume that are linearly independent x1, x2 at any point of R3. Now, this family is quasi-rectifiable if and only if for any point P, the integral tends to 0. So you calculate the limit with R to 0, this integral, which is the product of xi, xj. S is the one-dimensional sphere. D is the distribution spanned by these vector fields. If R tends to 0, the product of the vector field xi, xr tends to the normal. As a result of the, as a consequence of this theorem, we obtain the equivalent formulation that the family of linearly independent vector fields is quasi-rectifiable if and only if for the index I and j different, 1, 2, 3, if the curl of the product of the vector field xi, xj is spanned by this vector field. So these two forms are, I will use them in future, and it is completely equivalent.
Yeah, sorry, I have a question. Are there conditions in higher dimensions for quasi-rectifiability?
They are. But here I'm limiting to three-dimensional space because I am concentrating about some application. You can do, and it is in the paper with Javier de Lucas. You can see we characterize algebra for partial Lie algebra, quasi-linear for Lie algebra for partial differential equation up to the dimension 5. It was done.
Okay, so it's not for arbitrary dimension. Okay,
it was for the it was for dimension 5 of the Lie algebra. But by the way, Michel, but expression 3.1, have you written this for vector fields on a manifold of larger dimension than 3? Because it looks like something with differential force. I mean, the stereo product does exist only on R3. So have you tried to generalize this formula 3.1 for vector fields on a manifold dimension larger than 3?
Okay, I will try. I didn't succeed. I can tell you that I use Poincaré lemma about cohomology to shrink to a point. It was, I have half a proof. I can demonstrate when we see each other.
No, it will be cool to know, to take a look. Okay?
Absolutely, I am agree. But this is a natural question.
Yeah, sure. Thank you, Michal. One day you can tell me. Thank you.
Okay, so let me next one. Now, I would like to illustrate our consideration for very simple examples. It's Euler, 1 plus 1 dimensional Euler system, non-stationary one, compressible, which is governed by 3 hyperbolic equations. So rho is the density, P is the pressure, U the velocity of the flow, kappa is the adiabatic exponent. So what you have to solve here, eigenvalue problem for this matrix that you see for this system. So V plus and V minus are the eigenvalue, gamma plus, gamma minus are the eigenvector for sound waves. V0 is the eigenvalue, and corresponding gamma 0 is eigenvector for the entropic wave. So we have 3 waves associated. Now, the vector fields, gamma, which I denoted gamma plus, gamma 0, gamma minus, are linearly independent at any point R. Now, let me introduce the basic solution. It was done by Riemann 200 years ago. So you have entropic wave denoted by A. The rho only change, P and U are constant. Rho satisfy the partial differential equation rho x plus U rho t plus rho x equal to 0. Now, the sound wave, S plus, S minus. So P and U are parameterized by rho. Rho played the role of Riemann invariant. Here A and P and U0 are some constant, and rho satisfied the equation which I wrote in abbreviated way, rho t, the eigenvalue for sound waves multiplied by rho x equal to 0. That is the Riemann simple waves. So what was done by Riemann, he was interesting. to look for elastic superposition of waves. So the commutator relation for the vector gamma plus gamma minus is given by the following relation, that is linear combination of these two fields, gamma plus and gamma minus, with a constant coefficient which depends only on the adiabatic exponent. Now, so the vector fields gamma plus gamma minus is quasi-rectifiable, are quasi-rectifiable vectors, and they commute between themselves. So you can find a double wave solution which parameterizes the region of elastic superposition. And this is given by the expression U, P, and rho in terms of Riemann invariant R1, R2. So you substitute this relation into the equation, and you reduce to the system which is called in Riemann invariant or hydrodynamic systems, only for Riemann wave, only for double waves. Now, what you can say about this? If you give the initial data small, I will say y, compact and disjoint, there exists a time when the wave separate. So you give this initial data that small as compact and disjoint, and there is a time when this wave separate into same type of wave that we impose in the initial data. That's what I wrote, and this was observed by Riemann himself. He wrote about propagation of waves with small amplitude. That is what is about it. And here you have the picture, you have the data. We give the data in the intervals here AB, one, compact and disjoint. They propagate along the characteristic. Next, you have time t minimum, where the when the wave you have the superposition, and t maximum when the wave separates. You have the region of superposition, which is called M. T is the time t. If the characteristic of the same family intersects, you have the gradient cut, so-called gradient catastrophe. It means that the derivative of a known function becomes infinite. So the solution loses their sense. That's what I want to say about this situation. Now I would like to discuss the new element, which is a non-elastic wave superpositions. Now, the vector fields gamma minus, gamma 0, gamma plus, associated with Euler system does not constitute a quasi-rectifiable family of vector fields according to the definition. If you look at the commutator relations, gamma plus minus with gamma 0, it's a linear combination of this field with non-constant coefficients, which depends on the density, rho. Now, the natural question, what can be said about non-elastic superposition? So we have here the following Lie module. You have the maximal Lie module corresponding to non-elastic superposition of wave. It's generated by gamma minus, gamma 0, gamma plus. You have intermediate Lie module, which is correspond to double wave, which I just discussed, which is spanned by gamma plus, gamma minus. And you have the smallest Lie module, which correspond to simple Riemann waves, gamma plus, gamma 0, gamma minus, which have already been discussed. So I will concentrate on the first case, on the maximal Lie module for this case. So in what follows, I will identify the C infinity Lie module gamma plus, gamma minus, gamma 0, which correspond to the Euler system with infinite dimensional Lie algebra. And we have the following theorem. The smallest Lie algebra containing the vector fields gamma plus, gamma 0, gamma minus is isomorphic to the algebra calligraphic K, which is the semi-direct sum of the Abelian ideal I and three-dimensional Lie algebra K, which is a direct sum of non-Abelian two-dimensional Lie algebra, which is affine algebra A2, and one-dimensional Lie algebra. And we have a similar for H. I will give one. Now, the Abelian ideal gamma is spun by the vector field, which is gamma minus, I denote, the difference of gamma minus, gamma plus, and multiply by consecutive multiplication by rho to the power -1, -2, it's infinite. So it's the Abelian idea, infinite dimensional Lie algebra. Okay, now a few words how to understand this decomposition. Due to the fact that K, the calligraphic K, that Abelian ideal is included in calligraphic K, with the whole qualitative behavior of superposition of way is encoded in the algebra K, capital K. The quantitative part of the interaction of waves with varying rho is encoded in the component of the infinite dimensional Lie algebra I. The calligraphic algebra K contains the higher interaction corresponding to the sequence of superposition. That's how to understand. Now, during this analysis, we found an interesting result. This interesting result is not related to Euler system, but I would like to mention the one. Why? I will say later. The smallest Lie algebra containing the vector fields gamma 0, gamma plus, gamma minus, and consecutive multiplication by rho to the power minus, and that is all integers, is isomorphic to Virasoro algebra. It's a semi-direct sum of two Abelian ideals with the width algebra. So that's one result. And the second one is the following. The smallest real algebra spanned in this case by two vector fields, gamma plus, gamma minus, and its consecutive multiplication by rho to the power n, where n is integer, is isomorphic also to some Virasoro algebra, where I is the Abelian algebra and semi-direct sum with the width algebra. We have these two results. Now, I would like to concentrate on the result for the obtained from the Euler system. We have the algebra K describing the qualitative behavior of superposition of weight obtained from transforming the initial module to in the angle preserving way. And we can we have the following term. If we apply the angle preserving transformation to Lie module spanned by gamma plus, gamma minus, gamma 0, corresponding to the Euler system, then we obtain a Lie algebra which is isomorphic to the algebra K. The proof is given here. Now, what is important of this? the algebra K can be rescaled and is quasi-rectifiable. So we can provide the parametrization of the region of the of non-elastic superposition of waves. So I will change the base. So I choose the new base, V1 and V2, with the sum and the difference of gamma plus and gamma minus. The family of vector fields V1, V2, and gamma 0 is quasi-rectifiable. So I will determine the rescale function for these vector fields, V1, V2, and gamma 0. Once I did, I used the rescaling theorem to find the parametrization of the region of non-elastic superposition is given here in the last expression here. Now, let S1 be a manifold parametrized by F. Let S2 be a manifold parametrized as a logarithm of S1. So here you don't see. No, I can. The beta of T1, T2, T3 equal logarithm of the parametrization F of T1, T3. Let me define two quasi-rectifiable surfaces, phi and sigma, phi spanned by gamma plus and gamma minus, and given in parametric form, and sigma of T3, spanned by d beta with d beta T1 and d beta T2, and given in parametric form. Now we have the following theorem. The manifold S1 and the transform manifold S2 by logarithm can describe the non-elastic superposition of waves associated to gamma plus, gamma minus, gamma plus for the Euler system, and can be described by a parallel transport of quasi-rectifiable surfaces phi and sigma. So S1 is the sum of disjoint surfaces phi3, and S2 is the sum of disjoint surfaces sigma. The evolution of the surfaces F3 is completely defined by the evolution of sigma. Here you have a picture. I did a picture. So you have S1, manifold S1, 3 dimensions. So you slice the manifold S1 into a stack of quasi-rectifiable surfaces phi3, and you have the evolution along the vector gamma 0. And the similar for sigma 3, for S2. Now, as the quasi-rectified surface phi3 and sigma 3 I can write in parametrical form, which is given here, I can calculate the first and second fundamental forms and calculate the curvatures. So the Gaussian curvature for both are 0. The mean curvature is equal to 1.5, so it's flat. Next, so using the fact that using the parametrization of which correspond to non-elastic superposition of 3 waves for the Euler system, which is given the first expression, we can reduce the Euler system to reduce form to the 3 hyperbolic equation with unknown function T1, T2, T3 of T and X, and is given by the equation 10(1). So the right-hand side, the first and third matrix is the transition matrices. The second matrix, you have diagonal matrices, which is the eigenvalues. The the element which enter H2 and H0 are the scale function which correspond to the difference of vector fields gamma plus, gamma minus, and gamma 0. So taking into account now the eigenvalues which I provide, I can find the reduced form of the Euler system. This is for the specific case, when the adiabatic exponent kappa is equal to 3. So what you obtain a simpler form than we obtain a simpler form than the Euler system, which correspond to superposition of 3 waves. So the solution of the 2 waves, one of them the sound wave, S plus or S minus, with entropic, results in the superposition, give a produce a third wave. This is a necessary condition, not sufficient one, I have to say. Now, I would like to mention something about the reference. The first reference is due to Peradzinski, to result that where he found the necessary sufficient condition. The next two is with collaboration with Javier de Lucas concerning quasi-rectifiable Lie algebra for partial differential equation. And second one is a multi-Riemann wave for the most general form of partial differential equations, where we define the rescaling theorem. Next two references due to Riemann, where he discussed simple and double waves. Now, the two next references is related to only it's in archive, is not published, the result with my postdoc, Romania, which we discuss the Lie modules analysis for certain type of hydrodynamic type system. The next one, it's my paper concerning the K-wave solutions, where I discuss elastic superposition, and I found also elastic superposition, which cannot be written in Riemann invariant, where I use conditional symmetries. For in magnetohydrodynamic, we have explicit examples. Next, you have Numizu theorem, which I didn't provide. There is some results about this surface S2, which is torsion-free with affine connection, not Levi-Civita. Next, you have two reference, interesting one, which refer to physics, to experiment, plasma physics, where they, in camera, they observe the evolution of ion sound wave with entropic waves, and when they prove that you have production of new sound waves. One of the, in the last reference, they said there are much more non-elastic superposition of waves than the elastic one. The elastic superposition are very rare. So I would like to end up with this, my talk.
So thank you, Michel, for your interesting talk. Is there any question, remark, comments about for our speaker?
I have two questions. Could you go back to slide number 29?
Which slide?
29.
29, I don't know which is 29, but you will tell me when I arrive.
This is the place where you parameterize, yeah, for instance here.
When I parameterize, it would be
yeah,
here.
Sigma and phi. You do it using the T3 parameter, but you can also choose T1 or T2, right, to parameterize.
Right. I choose T3.
Yeah, and why is that?
I can explain to this because you see, T3 is related with gamma 0. Omega 1 and omega 2 is related to gamma, the difference of gamma plus and gamma minus, or the sum. That is only why I did in this way.
Okay, so it has to be T3.
Yeah, it has to be T3, exactly.
Okay. And the second question is how much more complicated it gets when you consider a more dimensional example.
Okay, I will answer to it. I know the answer to this. You see, I have to go to the first one of my first slide, where I wrote the involutivity condition, which was found by Zbigniew Paradzinski. This involutivity condition is for to extract the elastic superposition. So you have weakened them. I will be here. Okay. So the demand that the Lie derivative of covector lambda along vector gamma be spanned by the two vector lambda, of course in 2 dimensions is automatically identically satisfied. You have weakened the one. There are different ways to do it, because you have what we are doing. You in the stock you require this. You subject the initial system with differential constraints. So du have to be linear combination of vector field gamma and lambda, which satisfy the eigenvalue with non-constant coefficient. So where you have the compatibility condition, because you have first derivative and right-hand side is algebraic. And now how you derive the involutivity conditions? You look for that is exact differential in the sense of Cartan. So you take the differential du, which is, and you look for prolonged system. So du, and you write which called the so-called polar system, which have some free parameters you have to calculate, and you calculate a quasi Cartan numbers, and you it proves the involutivity. So you have to redo this system, but find a weakened condition for lambda. For example, it could be as not necessary that the sum of this vector fields, so it means the derivative of this Lie derivative of the lambda along the vector fields is spanned by this field, but not only this field, but by more. That is a Lie module. And you have to analyze this Lie module. It's one way to do it. There are another way where you can obtain to weaken these conditions. That is how you can apply to any dimension.
Okay, thank you. Thank you.
Any other question? Well, I'll make one, a difficult one. Michel, imagine that you want to generalize these polyhedras that are not non-elastic, yeah?
Yes.
Which is the first example you could try to apply this method to? One that it will be non-elastic, it will be interesting, and it will not be that crazy, that difficult to check whether we are able to do anything. What will you try to apply it?
Okay, I can tell you. First of all, I choose the example that we did together when it was analyzed for elastic one, where you give. For me, it was a natural question how to generalize for non-elastic. Of course, non-elastic wave superposition appear in a plasma physics and especially in magnetohydrodynamics. Magnetohydrodynamics admits the following waves: entropic waves, like in hydrodynamics, two Alfvén waves, which is not in hydrodynamics due to the presence of the magnetic fields, and magnetoacoustic waves, four of them, depends on slow and fast. So you have seven type of waves. So you can calculate for them the commutator relation. And some, for example, is you have the if the magnetic fields have one component, the magnetoacoustic wave, F, let us call the F plus F minus, because it's a fast one, are elastic. But if you calculate with them, if you introduce the entropic wave, and you have entropic wave with magnetoacoustic, you obtain non-elastic, and you have about seven types of not seven, six types. Sorry. Six type of Lie modules depends on the configuration of the magnetic fields. It's first you have to understand the most simpler case in before to go to many dimension. This I will start with in 1+1 dimensional magnetohydrodynamics.
Okay, for these equations, do you know any known solutions? Exact solutions you can try to retrieve.
Okay, exact solutions for elastic, there was done, it's a Polish school, I have to admit. It was start with Peradzyński and Burnat and Wojciech Zajączkowski. And Wojciech Zajączkowski found for magnetohydrodynamics equation in 3+1 dimension, he classified all of them elastic superposition. That it was a tremendous work, and it was his PhD thesis. Very interesting one. After this, there was some, I would say, attempt to find some solution, numerically or asymptotically. This was, such a try was done by Brettel and Peradzyński, but never been published. I don't have this, but I know from a seminar when I were in Poland.
Okay, thank you. But Michal, we have to try one day to do this in the short.
Yeah, we have to be together and to develop this. I am completely alone and working now on it.
Okay, so it would be fine to talk about it because it seems something very interesting.
Yeah, I appreciate very much your invitation and always discussing with you. Thank you very much. And thank you, the audience, for question and your attention.
Thank you too. So now we can finish. Thank you, everyone. And we'll see you in a week. We have Salnikov.
So be in touch with me.
Yeah, sure, Michal. I will call you. Thank you, everyone.
Okay.
See ya.
Thank you very much for the talk. Yeah. Bye-bye.